Now let me try to explain the importance of the unit circle in understanding the trigonometric functions. First of all, one very important triangle that you have to know is the right triangle that has the hypotenuse length as 1. So let's say you have a right triangle whose hypotenuse is length 1, and let's also say that the angle on right here is equal to theta. And then because we don't know the length of the base and the height, let's just name it as x and y for now. And from here we can think about the sine, cosine, and tangent as just as what we did before. So apply the SOHCAHTOA. Sine of theta is opposite over hypotenuse. Opposite of the theta is y. Hypotenuse is 1, so that's equal to y. Or another way to say this is that y happens to be sine of theta. Okay, and then if we do the cosine of theta, adjacent of the angle theta is x, and since cosine is adjacent of hypotenuse, we have to divide the adjacent by the hypotenuse, which is 1, so that's equal to x. Again, that means that x is equal to cosine of theta. Now, this immediately tells us a very interesting discovery, that if you have a right triangle of hypotenuse 1 and angle theta, then the base length becomes cosine of theta, and the height becomes sine of theta in this picture. And this is a picture that you should memorize. It's very important. Why is this important? Well, it has a few uses. So the first thing that you can get from this picture is that if you apply the Pythagorean Theorem, cosine theta squared plus sine theta squared is equal to 1 squared. Now it happens that later on, when you use trigonometric functions a lot, there are many occasions where you have to square the cosine function and square the sine function, and because it's cumbersome to write parentheses all the time whenever you have to square it, people, instead of writing cosine theta squared like this, they write it as cosine squared of theta and sine squared of theta, and 1 squared is 1. Now you might wonder, why not just write down cosine theta squared? Well, that has a totally different meaning. Cosine theta squared is not the same as cosine theta parenthesis squared. This really means cosine of theta squared. And again, cosine squared theta is the one that we will take it to mean cosine theta squared. So it's very important that you know this shorthand. So whenever you see cosine squared, tangent squared, whatever trig function squared equal to, inside one equation, you should first think of it as equal to cosine theta parenthesis squared. Okay, so this is a very important formula in trigonometric functions, and this equation just comes from this picture. Now, there's another very important formula that you need to know. That's by applying the SOHCAHTOA, T-O-A, tangent of theta is equal to opposite of angle theta, which is sine theta, over the adjacent, which is cosine of theta. So tangent theta is sine over cosine. That's another very important formula. So this single picture actually contains two very important formula that will be used many times when you are working with the trigonometric functions. And there's a third one which is not as important as the other two, but still nonetheless you're going to see it from time to time. The third one is if you think about the angle of the opposite side, that's 90 degrees minus theta, right? Because we already figured out that since this is 90 degrees, these two angles have to add up to 90 degrees. So these two are complementary angles. If this is angle theta, the other side has to be 90 degrees minus theta. Now, if you were to choose this one as the angle, then the role of the adjacent and the opposite exchanges. So what you used to call it as the opposite becomes the adjacent, and adjacent becomes the opposite. And because of that, sine of 90 degrees minus theta will become cosine of 90 degrees. No, cosine of theta. And cosine of 90 degrees minus theta will become sine of theta. These two formulas are called cofunction formulas. And that's actually, this formula is the reason why when you call one of the ratio as sine, the other side is called the cosine. The reason that you use this co is because of this identity. So sine of the complementary angle is same as the cosine of that angle. That's why you use this co. It probably comes from the word complementary. Now, you actually have seen this at work before. So in the last video, I concluded with this table. As you can see in this table, sine of 30 degrees is same as cosine of 90 minus 30 degrees, which is this one, right? And cosine of 30 degrees, which is square root of 3 over 2, is same as sine of 60 degrees, which is 90 minus 30 degrees. So these two are the same, these two are the same. And also, sine of 45 degrees, according to the cofunction formula, is same as cosine of 90 minus 45, but 90 minus 45 is exactly 45 degrees. Maybe I should write that. Okay. So according to this cofunction formula, cosine of 90 degrees minus theta is sine of theta. What does that mean when you have 45 degrees for theta? 90 degrees minus 45 degrees is sine of 45 degrees. And then 90 minus 45 is 45 degrees. So cosine of 45 degrees is same as sine of 45 degrees. So they are the same. And that's the reason why in this table you see that the two are the same. Okay, back to this picture here. So now you see that this single picture contains three formulas that you didn't know. Well, if this is a review, then you probably knew this before, but it contains three formulas that's very important in trigonometry in this single picture. So that's why this picture is very important. Okay, not only that, we can use this picture to extend the definition of sines and cosines beyond the triangles. So what I'm trying to say is that, for example, if we just use SOHCAHTOA, this is tied to a triangle, so it doesn't have any meaning if this angle becomes beyond 90 degrees, because if this angle becomes beyond 90 degrees, then you can't think about a right triangle that can have something bigger than 90 degrees. I mean, see, the other side is 90 minus this angle, so if this is bigger than 90 degrees, the other side becomes a negative angle, so such a triangle doesn't exist. So if you use SOHCAHTOA as the only definition of the trigonometric functions, then you're stuck with the sine, cosine tangents where it only will give you values between 0 to 90 degrees. But mathematicians quickly found out that it's important to have the sine, cosine, and tangents for something bigger than 90 degrees when they were trying to apply it to triangles that's not a right triangle. So even though we're only playing with right triangles, it turns out that you can talk about the usage of sine, cosine, and tangents for other generic triangles that's not 90-degree triangle, but you can have some kind of obtuse triangle or complementary triangle, obtuse triangle or acute triangle. For those triangles, you will have cases where you want to find the value of sine of angle bigger than 90 degrees. So it quickly became important to define sines and cosines to be something bigger than 90 degrees. And even later on, this trigonometric functions found usage beyond geometry, and we began to realize that it's important to know important to define sines and cosines beyond just the ones that are used in triangles, which are just angles less than 180 degrees, but for any angle you can define sines and cosines of that angle. Alright, so how do we do that? How do we define sines and cosines for angles bigger than 90 degrees? Well, that's when you use this triangle, this circle, which is called a unit circle. What's a unit circle? Unit circle is it's a circle of radius 1 centered at the origin. So this is the x-axis, that's the y-axis, and then this position is 1, this position is 1, this is -1, and this -1. So it's a radius 1 circle which is centered at the origin. Now if you have such a circle, then we can bring the previous picture, the triangle of hypotenuse 1, and we can make it fit exactly in here. Now why is this possible? It's possible because the hypotenuse of this triangle is 1, which is same as the radius of this circle. So that's an important picture. So to summarize, what I'm trying to say is if you have a hypotenuse length 1 triangle of one angle theta, then that triangle can be overlaid on the unit circle, and it's going to fit exactly. Now, because you're moving x to the right and y up, what's the coordinate of this position? The coordinate of this position is x comma y, right? But what was the value of x? We had the picture before. If the hypotenuse is 1, the x coordinate is cosine of theta, and the y coordinate is sine of theta. And that's good because now, although we can only draw right triangles on this side, but we can completely forget about the right triangle and just think about the angle and sines and cosines in the following way. So here's the new definition of sine and cosine. Well, it goes like this. If you're given any angle, it could be beyond 90 degrees. So let's say you're given something like 135 degrees, 135 degrees. If you're given that, then you can place that angle so that one side of that angle is on the positive x direction, and you can fit it right here. And the other side of the angle forms a ray that's coming out from the center. That ray, when you make it come out from the center, it's going to hit the unit circle at some point, right? It's going to have two coordinates, x comma y. Well, then whatever that x and y coordinate is, that can be obtained by measuring this length. If you drew this unit circle very, very carefully, then then you can figure out that this what this length is, what that length is. And because we decide to say call the x coordinate as cosine theta and y coordinate as sine theta, that was what happened for the case when we had the right triangle. So even in the generic case, we're just going to say the x coordinate is the cosine of 135 degrees and the y coordinate is sine of 135 degrees. I need to make this a little bigger. Sorry. Okay. So erase this, and let me write it here. So this point here is cosine 135 degrees, comma sine 135 degrees. Okay. So in general, if you have any angle, for any given angle, you place that angle on this unit circle. So let's say the given angle is something like this, then make that angle to have one side aligned to the positive x and the other side to emit a ray, so that when this ray is coming out from the origin, it's going to hit the unit circle at certain x and y positions, and therefore the x position will be called cosine theta and the y position will be called sine theta. Okay, what are some of the consequences of this definition? Well, if you know the coordinate system, the coordinate system, the plane, when you're given the coordinate system, we have named these coordinate systems into 4 parts. We call that as quadrants. So the first quadrant is this part, second quadrant is here, the third quadrant is here, and the fourth quadrant is here. Now, if your angle fits in the first quadrant, then we know that the x and y values are both positive in the first quadrant. So in the first quadrant, both sine is positive and cosine is positive. Okay. And then in the second quadrant, see this -1 here? That means x is becoming -1. So if you have any angle that's in the second quadrant like this, then we know that the cosine value becomes negative here, whereas the sine is still positive because it's above the x-axis. So this side, y is positive, this side, y is negative. On the right side, x is positive. On the left side, x is negative. And because x is same as cosine, we see that cosine of angle theta is negative if your angle is between 90 degrees to 180 degrees. Okay, now if your angle is an angle that's between 180 to 270, if your angle is something like this, so that your ray hits the circle at the third quadrant, in here both x and y are negative, so we know that sine theta and cosine theta are both negative. And then if your angle happens to be hitting here, if the ray happens to hit the unit circle here, then your cosine theta will be positive and sine theta will be negative. Okay. In addition to this, you also have the tangent. Remember, tangent is sine over cosine. We just did that. So if sine and cosine is both positive, then we know that tangent is positive. If sine and cosine is, sine is positive and cosine is negative, then tangent is negative. If sine and cosine are both negative, then negative over negative is positive. So tangent is positive. And over here, if you work out the sine, tangent becomes negative. all this is very confusing. So instead of trying to figure this out every time when you have to, a nice thing to do is to just remember which one is positive. So of sine, cosine, tangent, it turns out that on the first quadrant, all of them are positive. In the second quadrant, only the sine is positive. In the third quadrant, only the tangent is positive. And the fourth quadrant, cosine is positive. So S means sine is positive, and the other two, the cosine and tangent, is negative. And T means sine is negative, cosine is negative, only tangent is positive. C means only cosine is positive, and sine and tangents are negative. And you can memorize this as ASTC, but I think you can think of this ASTC as some kind of an acronym. You can make any kind of funny sentences if you like, but I think one of the most standard things that people use is they say all students take calculus. Okay, so that's how you remember this ASTC, all students take calculus.